Okay, thank you. So, let's continue where we left off. So, I'm just writing down all the partitions of 6 that we wrote last time, and we're going to come back to that later on. Okay, so recall. So, recall what we did last time. So, Pn is the number of partitions of size n, right? And we proved this theorem due to Euler that the sum n greater than or equal to 0 Pn x power n is given by this beautiful product formula, right? We proved this last time. So, what was the idea? You expand each of these factors as a geometric series and you look at the coefficient of any x power n, right? And to each term that contributes to x power n, you can associate a partition of n in a very natural way, right? So, that was the idea. Okay. So, before I move on to that teaser that I gave you about odd and distinct partitions, let me mention 2 generalizations of this. Okay. So, suppose, so 2 generalizations. So, first, suppose we only allow partitions with parts belonging to a set S, which is a subset of the natural numbers, including 0. And we have to make sure that 0 is an element of S, otherwise we run into trouble. So let's say we can allow, for example, all the primes, right? So suppose I want to find the generating function of partitions where I only allow, I mean, I can choose whatever I like. So let's say I only allow partitions containing 1 and 2, let's say, I can do that, or all the primes, or anything, only composites, whatever you want. You can make any restriction that you want. Then the same strategy of our proof will tell us. So let's say P sub S of n be the number of such partitions. Then the same proof that we did yesterday will show us that the generating function Ps of n, n equal to 0 to infinity, x power n, will become the product of j in S 1 by 1 minus x power j. So this is a special case where S is all of the natural numbers. So by natural numbers I mean let's say union 0. Let's say I'll call it n0, right? So it's natural numbers union 0. So if I allow my S to be everything, all the entire collection, then in this factor I get all the numbers, right? 1 minus x. Okay, maybe this is confusing because I don't want S to contain, I don't want to take j equal to 0 because then I'll get 1 minus 1, which is 0. So okay, Okay, forget this. I think this is okay. So I allow partitions from some set of natural numbers, right? 1, 2, 3, 4, etc. And if I only want to count partitions of, let's say, 1 and 2, so let's do odd numbers. So let S be the odd numbers, 1, 3, 5, etc. Okay. Then the right hand side is the product j equal to 1 to infinity, 1 by 1 minus x to the 2j plus 1 or 2j minus 1. Right? I am just taking the odd powers here. Right? So let's just expand this and see. So my first term will be 1 plus x squared plus etc. My second term will be 1 plus x cubed plus x to the 6 plus etc. Right? The third term will be 1 plus x to the 5 plus x to the 10 plus etc. Right? Etc. Right? So now if you see these, so if you just recall what we did from last time, any factor that comes from here will count how many times what 1 appears, right? Exactly. Any factor that comes from here will tell us how many times 3 appears, how many times 5 appears, and so on. So for example, 6, right? So look at x power 6. So to get x power 6, we cannot get 6 because there is no, I mean, we are only allowing odd parts. So we will get this one, 5, 1. So how do we get 5, 1? I will get 1 x power 5 and 1 x, right? How will I get 3, 3? 3 from 1 and no. Yeah, that's right. So it's this factor because I'm looking at the second factor from x cubed, the term corresponding to x cubed. Right? I mean, so this is parts for 3, part 1, this one is parts corresponding to 5. So this will be x to the 6 and 1 from everywhere else, right? That is corresponding to 3, 3, right? And similarly 3, 1, 1, 1 will have a 3 here and an x cubed here, 3 and 1, 1, 1 from here. And lastly 1, 1, 1, 1, 1 will come from x to the 6 here, right? You see that? So this is basically the same proof that we did last time except for any set. So I can do whatever I want. I can count partitions from any collection of natural numbers, finite or infinite, that I like, right? So x to the 6 we will get, so we get 4 terms, these 4 that I have circled, right? Is this clear? So this generalizes in one way. So the second generalization is, suppose we allow every part to occur, let us say k, at most k times. Okay, for some fixed k. Okay, so for example, if I fix k equal to 3, then I can allow a partition like this, but I cannot allow a partition like this because 1 occurs 4 times, and 4 is greater than 3, right? So if I put that restriction, and so if I let P upper k of n be the number of such partitions, then we get that the generating function of such partition P upper k of n see here, this is a geometric series. I'm allowing any part to occur any number of times. One can appear 10 times or 3 times or 1,000,000 times, it doesn't matter, right? I allow all of them. But now I fix k, so basically I have to truncate this geometric series up to, no, but here I'm talking about k, up to x bar k, right? Exactly what you said. So this is now a product j equal to 1 to infinity, 1 plus x plus etc. up to x bar j. Right? So it's the same idea. Is that, you have a question? Oh, thank you. Sorry. Yeah. X bar j. Thank you. Yeah, I was being sloppy. Let's go slowly. X bar j plus x bar 2j plus up to x bar kj. Okay. So how does this look like? So the first term will be 1 plus x plus up to x bar j. X bar k. Then times 1 plus x squared plus up to plus x to the 4th plus up to x to the 2k times 1 plus x cubed plus up to x to the 3k and so on. Right? This is how it's going to look like. So now you see any term that comes from here, so this factor will correspond to partitions with, this will correspond to the parts 1, right? And 1 can occur only at most k times. And here 2 can occur at most k times, so which gives you 2k, the quantity 2k and 3k like that and so on. Okay? So the same proof that Euler gave allows us to give these two huge generalizations. I can restrict the parts that I am allowed to take. I can restrict the number of times each part is allowed to come. Okay? This is of course a finite geometric series, so you can write it also as a ratio. That's also okay, right? But is this clear? So these are two generalizations of Euler's theorem which are almost immediate. Okay, so let me see. Now I think I should be able to state and prove Euler's theorem, Euler's odd equals distinct theorem. So this is Euler, if you just say Euler's theorem, there are so many things that appear in so many parts of mathematics, so it's better to qualify. So Euler's odd equals distinct theorem says the following. So let's say d of n be the number of partitions of n into distinct parts and O of n be the number of partitions of n into odd parts. So distinct parts means each part is distinct, it's not repeated. And odd parts means every part is odd. So then PD of n equals PO of n. D of n equals O of n for all n. Okay, so you remember towards the end of yesterday's class we did this, we looked at odd parts, odd partitions, so these are the 4 ones, and the distinct ones are 6, 5, 1, 4, 2 and 3, 2, 1, exactly, and these are both 4, right. So these are distinct and these are odd. Right. So let's prove it. And you will see you'll see the proof is essentially 2 lines. We have done all the hard work to. So let us look at the generating functions, right. So look at these two generalizations and tell me what is the generating function of d of n, or let us start with O of n. So n equal to 0 to infinity, O of n x bar n, what is this equal to? So it's a product, we allow all odd parts, right? No, no, odd parts, not distinct parts. Yeah, this one, I have already written it. These are the partitions into odd parts, right? Because we just saw, right? I did it with this example, 5, 1, 3, 3 and all that. So this is exactly this generating function, right? So this is the product j equal to 1 to infinity 1 by 1 minus x to the 2j minus 1, right? This is what we have. Now similarly, can you tell me what is the generating function for d of n? Yeah, that's right. So here this is exactly k equal to 1, because we allow each part to appear at most once, there are no repeats, right. So this is exactly, so d of n is just another notation of for p of p super 1 of n. So this is exactly product j equals 1 to infinity 1 plus x to the j, right, because we only allow it to occur once. So x cubed can only occur once, x fourth can only occur once, etc. Right. So now, but this is very strange. Here I have 1 by 1 minus x bar 2j minus 1, here I have 1 plus x bar j. These two don't look the same. But Euler is telling us that for every n these are the same. So as formal power series, these two have to be same. So what is going on? Can anyone see? So say that again.
1 plus 2x plus 4x square equal to 1 by 1 plus minus 2x, right?
Yes.
We can use a similar one here
How?
because the product expansion can be.
No, but if you see this way, here each term is an infinite product, infinite sum, right? This is a geometric series.
Okay.
But here this is just a finite sum, it's just two terms.
Okay.
Right? Can anyone see? Does anybody have an idea? It's very simple. But you know, it's very simple once you see it. I mean, before that maybe it's not so clear, right? I mean, these two look very different. One has numerator, one has denominator, one is infinite, one is finite. What's going on? So the trick here, let me do it over here. So look at product j equals 1 to infinity 1 plus x bar j, right. What I will do is I will multiply and divide by 1 minus x bar j, okay. I am allowed to do that, yes, okay. So now what do I get? So this is the proof. Product j equals 1 to infinity, what do I get upstairs? 1 minus x bar 2j and 1 minus x bar j, yes. So let us look, let us look more carefully at this. I will just write the individual terms. We will write the first few terms. I have 1 minus, what is the first term? 1 minus x squared, x4, etc. And in the denominator, 1 minus x, 1 minus x squared, 1 minus x cubed, etc. Now you see what's happening. Can I cancel some things? What can I cancel? All the even powers I can cancel. Here this will cancel with here and so on. So in the numerator you will be left with nothing, all the factors are cancelled. And what is left in the denominator? Odd powers. This is product j equals 1 to infinity 1 by 1 minus x to the 2j. Finished. End of proof. Essentially 2 lines. Right? So this is the way Euler proved it. But yeah, it's brilliant. But it's not satisfactory. I mean, it does not explain to us why these two are the same, right? I mean, it's a proof. No one is disputing that it's a proof. But we want to understand it better. Like so to understand it better, people wanted to give a bijective proof. So let me do that now. So there was this English mathematician called Gleicher. He gave a bijective proof. This. Okay. So we are going to see this bijection in action. Okay. So the idea is this. So which way do you want to go? Let's say so what he did is so let's introduce some notation. So let's say capital D of n is the set of distinct partitions of n. And capital O of n is a set of odd partitions of n. Okay. So Gleicher constructed a function f from D of n, or let's say O of n to D of n, which I'll describe now. So we'll prove that it's a bijection. So the idea is, so suppose lambda is a partition, right? I said we use this notation lambda. It's lambda 1 to lambda k. So this belongs to, let's say, O of n. That means the size of lambda is n, and all the parts of lambda are odd, right? They are only odd integers. Each of the lambda is odd. Okay. So what he said is whenever, so replace let's say two occurrence, let's say replace lambda I comma lambda I plus 1. Okay, let me say that again. Okay, let's start again. So if lambda I equals lambda j, lambda I plus 1 is, if they are equal to some odd integer 2k plus 1, then replace lambda I comma lambda I plus 1 by twice 2k plus 1. You double it. And a single part, you put a single part there, okay? And repeat. So this is the first step. So let's say 1, to repeat 1 until all parts are distinct. Right? So anytime you see two parts being equal, you squash them together. You kind of combine them into a single part with double the value. Okay? And the only way this process will stop is if there is no repeats. But that means it's a distinct partition. Right? So this will do what we want. Right? So then we get at the end, this gives a thus f of lambda belongs to D of n, gives a distinct partition, right? You just keep grouping things together. So let us see how this works for this example. So for n equals 6, we have these 4 odd partitions. So O of 6, I have 5, 1, 3, 3, 3, 1, 1, 1, and 1, 1, 1, 1. Right? So what is f of lambda? So what will it do to 5, 1? It will remain same because it's already distinct, right? So if the partition is already distinct, you cannot do anything, right? There is nothing to do. So here I will get back 5, 1. There was nothing to do. Here are there repeated parts? Yes, 3 is repeated. So what will I replace 3, 3 by? 6, because I will add these two and the process stops. Okay? Is this clear? Now what will I do here? 3 is distinct, it occurs only once, so I don't do anything. 1 occurs 3 times, so take 2 of the 1s and replace them by 2. And now you get 3, 2, 1 which is distinct. So in one step we are done. So in both these cases in one step we are done. Here it's a little more complicated because there is an intermediate partition. So these two I combine and these two and these two, so I get 2, 2, 2. But is this distinct? No. But I take 2 of the 2's and I combine them and I get 4, 2, which is distinct. And these are the 4. Okay. So it's a nice elegant bijection and natural. And the question is, what is F inverse? How do you, so let's describe F inverse. So to prove that this is a bijection, I have to come up with an inverse map, right? Which takes a distinct partition, odd partition. So what do I do? What do you think I should do? Just look at this example and see. Right, exactly. So every time you see an even number, you even part, you replace it by half that number 2 times. Okay. So here, so let's say 1. So if lambda I equals to k, replace lambda I by k comma k, 2 parts. Of course this could still be even, right? If I take 4 or whatever, if I take 8, I will get 4 comma 4. That's not good enough. So I have to go back, I have to repeat. So then I do the same thing. So repeat 1. And when does this process stop? If there are no even parts, which means they are all odd parts. So repeat 1 until all parts are odd. Right? So then F inverse lambda belongs to O of n. And it's easy to see, okay, you just have to check a few things, but it's easy to see that this is the inverse of that, right? Because here you combined equal things to get, whenever you replace 2 occurrences of the same integer by double that integer, the double integer is automatically even, right? And so the reverse process is when you get an even number, you split it into 2, right? So this gives a proof, a direct bijective proof that these two are the same, right? So although this generating function proof is a proof, it is correct. I mean it says that these two things are equal, but it's not satisfactory in some sense because it doesn't explain to us why that's true. But this Gleicher's bijection explains to us why these two sets are the same, right? Okay. So this is actually, I mean, because this, in mathematics, whenever you have a beautiful result, people try different ways of explaining that result. So Gleicher tried one way. There is another bijection which I will explain very soon, which says more, which gives us more insight into this connection. I'll come to that in a second. So now I want to explain another bijection, and I want to ask you to prove it. It's not difficult, but it requires a neat idea. So here is another theorem, okay, or it's easy, so I'll call it a proposition. So the number of partitions of n into k parts, okay, I just I mean I take all possible partitions, not odd or distinct. You can forget about odd and distinct for now. So I just demand that there are k parts, k is some fixed number, is equal to the number of partitions of n with largest part k. Okay. In one case I am saying that you are only allowed k parts, k is fixed. Okay. And the other case I am saying you only consider partitions where k is the largest part. It could repeat, but there is no part larger than k. Okay. These are different things, right? You see that they are not the same. So what happens if k equal to n in the first case? How many partitions are there of n into n parts? No, that's correct. Let's just check. So if, what is it? Right. If I want a partition of n into n parts, all of them have to be 1. Okay. And how many partitions are there of n with largest part n? Only n, singleton n. You cannot do anything else, right? Otherwise that will overshoot. It will become larger than n, right? So at least in this simple case they are the same. Okay. Let's check some other examples here, and then I want you to think about why this is true. So let's do n equals 6. Let's do k equal to 3, for example. So what are the partitions with exactly 3 parts? 2, 2, 2. So largest 3 parts. 2, 2, 2. 3, 2, 1. 4, 1, 1. Agree? These are all which have exactly 3 parts. And which are the partitions with largest part 3? 3, 3, 3, 2, 1, 3, 1, 1, 1. Okay, so the number is the same. What's going on? What is the idea? Can you see? What relates these two? Whenever it's
Whenever it's greater than k, we can take it as k plus some other term less than k. We can do that, continue doing that until we have k or less than k.
Say that again. Can you give it with an example?
So when, for example, in the three
Are you
parts,
starting from here or
yeah,
here?
I'm starting from 3 parts.
Okay.
So when I'm having 4.
Right.
So you're taking it as k plus something else.
So you're breaking this 4 as 3 plus 1.
Yeah, and so that will be
that'll come
next
here.
one.
But what do you do with less than k? That's a good idea. It mimics sort of what we did for Gleicher's bijection. That's good.
So
Sorry?
for maybe for less than 2, less than 3, whatever that's repeating, can we count the number of times, something like that?
Yeah, you're sort of on the right track. Yes, you had an idea? Just 1 second. Yeah.
If it's even, suppose say k is some number and then we are looking at the 3 parts. Here 4 is even and it's greater than k.
Yeah.
So if it is greater than k, then we are dividing it as k plus something.
That's what he said.
And if, and for the first part,
Huh.
2, it's even and it's less than k.
Yeah.
When we find such a number, we can just add 1, like the next.
From the next
partition.
one.
Yeah.
But then this will become 3, 1, 2. That's not a partition. And if you take it from here, then you'll again get 3, 2, 1. So then both of these will map to 3, 2, 1, right? That's tricky. So there's a new idea here. So let me explain the idea. So the idea is to have another representation of partitions. And this is called the Young diagram. So let me define it. So a Young diagram, the Young diagram of a partition lambda is a collection of boxes so that there are lambda I left justified boxes in row I. Okay, so let me show you how a partition will look like. Let's take as an example, let's take 4, 2, 2, 1. Okay, it's just I'm just taking some arbitrary partition. What is the Young diagram of this partition? So it says that I have to draw some boxes. In the first row there will be 4 boxes, okay, because the first part is 4. In the second row there will be 2 boxes, but where will I place them? They are left justified. So I have to start from the left. In the third row, again 2 boxes. Okay, and in the last row, in the fourth row, 1 box. Okay, this is called the Young diagram of a partition. Okay, everybody clear on the definition? Okay, so let me draw the Young diagrams for these 6 partitions, and then you should be able to see the connection between them. So this is 3 parts. So I have 2, 2, 2. So it looks like a rectangle, right? 2, 2, 2. Then I have 3, 2, 1, right? And then I have 4, 1, 1. Yes, this is on the left, and largest part 3. I have 3, 3, which is also a rectangle, 3, 2, 1, which is the same thing, and then I have 3, 1, 1, 1. Now do you see some connection? Huh? Translation. Translation just means moving. Yes? Perfect. So, can you say that? Can you give her the mic? Yeah, let her explain. Yeah. You can raise your hands.
Sir, if we look the three parts into vertically, we'll get the large partitions.
Okay, can you say that again? Look at vertically. Can you maybe let her explain?
Instead of seeing it horizontally, we have to take it account that vertical sections.
So say that again. So what would this? Where would this partition go?
It should go like 3 and 3.
3 and 3. So it will go here,
Yeah.
right?
Yes.
This will go here. So this is 2, 2, 2. Okay,
Yeah.
maybe it's just confusing. So I'll write it 2, 2, 2.
This is
3, 2, 1.
3 to 1.
That's the same thing here. This is 4, 1, 1.
4, 1, 1, 1.
And this is 3, 1, 1, 1.
1, 1.
And this is 3, 3. So what are you saying? So this is 2, 2, 2.
Yes, sir. Here in that largest part 3, let me just draw all these things.
Yeah.
And then we were
Oh,
seeing
here.
it like in the, we were just counting it in, taking the account to this row. If you're taking it into account the columns,
Yeah.
we will be getting that.
Right. So what she's saying is, here we read 3, 3. We counted how many boxes are there in each row, right? But she's saying, instead of counting it as a row 3, 3, you count the columns 2, 2, 2. You get this. Here, this is 3, 2, 1. But that's the same as 3, 2, 1 here. Right? That's a coincidence. And here, this would be 3, 1, 1, 1. But if you read it column wise, it is 4, 1, 1. Okay? So this is exactly the point. So that means if you had k parts over here, then the first column when you read, it will be k. If you have k parts, that means the first column has length k. And then it's decreasing, and first column is the largest part, right? Another way of saying it, do all of you know, did all of you study linear algebra? Do you know what symmetric matrix is? What is a symmetric matrix? A is equal to A? I do the transpose, right? So if I transpose the diagram, that means I reflect about the diagonal. Okay, so here is the diagonal and I reflect. So, so the bijection, the proof of this statement is the bijection that, okay, so let me just say it. So, given a partition lambda, the transpose or the conjugate partition denoted lambda prime is obtained by taking the transpose of the Young diagram of lambda. Yes? So, as an example, what is the transpose of that partition 4 to 1? So, you read the first column 3, 1, 1. So, this is 4, 3, 1, 1. Whose Young diagram is this? So, I have 4 in the first row, 3 in the second row, and then 1, 1. Right? Okay? And the proof of the proposition is bijective, bijection, which takes lambda to lambda transpose. Right? So, if a partition has k parts, then its conjugate will have largest part k. So it's, and vice versa, right? What happens if you do a conjugate 2 times? What is the conjugate of lambda conjugate? Original partition, right? It's an involution. When you do it twice, you get back the original. Okay, so this shows that the number of partitions of n into k parts is equal to the number of partitions of n with largest part k. Okay, so let's do something slightly harder. Okay, so I need a definition. So that's the end of proof. Okay. So we say that a partition is self-conjugate partition lambda is self-conjugate. What do you think it means? Lambda equal to lambda prime. It's like a symmetric matrix, right? It's the analog of that. So if lambda equal to lambda prime. Okay. So in all the partitions of 6, can you mentally construct the Young diagram and tell me which are the self-conjugate partitions? 3 to 1, yes, we saw that. That is self-conjugate, right? Anything else? No, 6 when you reflect, what will you get? 1, 1, 1, 1, yeah. So actually there is nothing else. So, but another example, so you might be worried that there are no other self-conjugate partitions. So one example of a self-conjugate partition is 4, 2, 1, 1. Not 4, 2, 2, 1, but 4, 2, 1, 1. So let's draw it. 4, 2, 1, 1. Right? Now you look at it column wise, you get the same thing, right? Or in other words, you reflect of this diagonal, it's the same thing. Okay? So now I ask you to prove the following result. And the hint is to use the Young diagram. Okay? Proposition. The number of self-conjugate partitions of n is equal to the number of partitions of n into odd distinct parts. So so odd equals distinct we have, but now I'm saying that we should only have odd parts, and every odd part should occur at most once into odd distinct parts. Okay, so for an example, again n equals 6. So 3 to 1 is the only self-conjugate partition. I have listed all the odd partitions. Which one of them have distinct parts? 5, 1. There is nothing else. Otherwise either 3 is repeated or 1 is repeated. Yes? So 5, 1 is the only has odd, is the only one with odd distinct part has. So can you think of the idea? Look at the Young diagram of 3 to 1, which is the only self-conjugate partition. Can you see what to do? No, do something more pictorial. Do some operation on the Young diagram. That's why I'm saying think geometrically. Think do something with the, manipulate the Young diagram in some way, I would say. It's not, okay, maybe not so easy. Okay, so let me show the idea. So suppose lambda is self conjugate. That means its Young diagram is something, whatever it is, it's complicated. But it's going to be symmetric about this reflection, right? So what we are going to do is we are going to construct what are called hooks. So we are going to go like, maybe I'll use another color. So we are going to go like so, we go down and right, and then we go the next one down from here and right, and like that, okay. So we keep building these hooks, okay. So, and so on. So for example, in this partition we have two hooks, one which goes like this and the other one which goes like that, okay. So what is the length of each hook? Now, what can you say about the length of each hook? In this case or in 3 to 1 case, which one are you doing? Yeah, so so that you see 5 1. So someone said what? Who said that? Okay. Yeah, very good. So it's always odd. Each hook length is always odd. Why? It's self conjugate. Remember, it's self conjugate. Look at this one. It's self conjugate, and the length of this hook is 7, which is an odd number. Here this is self conjugate. The number of things in this hook is 5.
The number of boxes in the row is equal to the number of boxes in the column.
Yes.
But the total number of boxes in the hook is the number of boxes plus in the row plus the number of boxes in the column minus 1.
Minus 1. Why
Number of
minus
boxes
1?
Because you're counting that corner box twice.
Right. So this box is coming twice, right? So this is k plus k minus 1. So that's 2k minus 1, which is an odd number, right? So every time you have a self conjugate partition, the idea is that you can break it up into these hooks, and then you can rearrange the hooks, right? You can stretch the hooks, you can sort of open it up and you can form a partition of this. And the other important thing is the distinct part. So this will say we have shown odd. What about distinct? All of these hooks, because it's a partition, that means there cannot be extra things here, right? So the largest possible, so if I have this, or let me come here, if I have this hook, the next hook can only start from here and end here. So in that case, it can have, it has to be necessarily a smaller odd number, it cannot be equal, right? So if I had drawn, for example, so if I have drawn 5 and I try to draw another 5 here, it will look like this, right? So this is 5 and this is also 5, but this is not a partition, right? It's so all each of the hooks will be necessarily smaller, right? So again this pictorial representation gives you a lot of information. Okay, so right, so now I want to just give you an idea of another bijection of the odd equals distinct theorem, which, as I promised you, gives more information. Okay. So I'll just give you the idea. I cannot prove it. It's quite technical. Sylvester's bijection for the odd equals distinct theorem. Okay, so the idea is the following. Okay, so you start with an odd partition. So let's say lambda is an odd partition. So we'll write the parts of lambda as hooks. Okay, so for example, let's take lambda equals 7, 5, 5, 1. Okay, there can be repeats, right? This is not this theorem. This is number of partitions with odd parts equals number of partitions with distinct parts. Okay, so what you do is you write hooks. So let me just show you on this example. It's a bit complicated. So this is 7. Then you write 5. I'll write it slightly off so that you can see what's going on. So this is 5. Then I have another 5. I've drawn this too big. So for now this would be a valid partition, but now it's going to not be okay. And then I have a 1. So this is, if I write it this way, this is not a partition, right? It's clear because there's this extra jutting out here, okay? And anyway, this has nothing to do with distinct parts. I mean, we started with an odd partition. I want to construct distinct part. So Sylvester had this beautiful idea. So what you do is you go diagonally like so, the first part, and you start from the corner, you go up and then you go right. Okay, so that will take care of this box, this and these. Okay. The next you start from the next diagonal below and go down. So you will go like so, then you go below. Okay. And then you go the other side. So this has taken care of this box, this. Okay. Now the first hook is completely taken care of. Now we go to the second hook. So we go like so and here. Okay. So that's taken care of this and this. And now you go like so and there. So that's taken care of these two. And lastly, you go like that. Okay, so it's quite complicated. And so the resulting, you count the lengths of all these things. So the first one was 1, 2, 3, 4, 5, 6, 7. We have already calculated 1, 2, 3, 4, 5. Then the green one is 3. Then the next white is 2. And the last red is another one. So it's a distinct, right? So the claim is that this will give a distinct, a partition with distinct parts, but more or less, moreover, it will give something stronger. How many distinct parts are here? 3, right? 5 is repeating. So number of distinct parts is 3. So Sylvester's bijection says that the number of odd partitions with k distinct parts is equal to the number of distinct partitions with k contiguous blocks. So what does that mean? So you look at what we got at the end and look how many are of the form I plus 1, I plus 2, I plus 3, I plus 4, etc. That's one contiguous block. So 3 to 1 is one block, right? They are all contiguous, one after the other. then 5, and then 7. So here you have 3 distinct parts, and here you have 3 contiguous blocks. Okay. So Sylvester's bijection, I have not proved it. This is much harder to prove. You have to write it down very carefully. But if you can do that, you get you get a refined statement for the odd equals distinct theorem. Okay. All right. So okay. So now I want to say something about the number of partitions. So we have given you a sheet of paper with the first 200 partitions. Just careful. Are you okay? Yeah. So does everybody have it? Yes. Okay. So I'll yeah, you can go ahead. No, let that. So one of the so you must have all heard of Srinivas Ramanujan, who of course had major contributions in mathematics, but in particular he had a lot of ideas, a lot of new results in partitions, in the theory of partitions, and I will tell you two of them soon. But one of the landmark achievements is a formula for the growth of Pn. How fast does P of n grow? Okay. So together with Hardy, they proved the asymptotic formula for Pn. So Pn grows like 1 by 4 root 3 e to the power square root of 2n by 3. I think that's correct. Let me just check. Times pi. Okay. So you see, so the growth is roughly, so the growth is like e to the square root of n, if you forget the constants. So it grows faster than any polynomial, but it grows slower than the exponential function. Okay. And so this is less than 2 to the n, because it has to be less than 2 to the n, because 2 to the n, well, 2 to the n minus 1 is the number of compositions, and as we saw yesterday, and partitions are a much smaller subset of compositions, right? So it should be certainly smaller than 2 to 2 power n, but the R.D. Ramanujan formula proves that it's grows like e to the square root of n, and moreover these numbers are exact, it's not approximate, right? So the ratio of these two numbers goes to 1. So you can see that if you plot those numbers given to you, it will grow not exponentially, but it will grow slower than that. Okay, if you plot this function compared to e to the n, you'll see it's slower, and if you compare it with any polynomial that you like, you'll see that this will be faster than that. Okay, so it's somewhere in between. Okay, and this is a consequence of something that they proved, which is quite an amazing result. So the story, okay, so the idea is that suppose I want to calculate P of 200, let's say the last number in your table, right? It's whatever, it's how many, is it billion or million? What is it roughly? 40 billion. What? Quadrillion. Okay, it's 3.9 trillion. Okay, so if I want to know P of 200, it's whatever, it's near 4 trillion. So I am allowed an error of a million, right? I mean, that seems like a lot, but compared to 4 trillion, how much is 1 million? I mean, it's about 0.0001%, right? It's a very small error. So I am allowed that kind of error. So when Hardy and Ramanujan were trying to find this formula, Hardy said we can allow for some error like that. So, but Ramanujan was convinced that there is a formula that will work on the nose. It will give you the number within plus or minus 1. Okay. So, the Hardy Ramanujan formula is a formula for P of n, which is a series, and for any integer it's going to sum, and it's going to give us something that is within plus or minus 1. So there is absolutely no error. Okay, if you take the integer part of that formula, you get exactly the number of partition, no error at all. Okay, so that's, and first Hardy refused to believe that such a formula can even exist, because the actual formula is quite complicated. Okay, but Ramanujan managed to construct a formula and then they proved it together. Okay, so this is one of the kind of romantic stories in this area. I mean, the fact that such a formula could even exist was not clear, and then so then there are further developments due to Rademacher and so on. Okay, good. Now I want you to stare at the sheet that I gave you and see if you can observe some patterns. So for each n, look at P of n, and I am not giving you any hints. See if you can observe any pattern for the numbers. I'll give you a minute. Any pattern at all is okay. Anybody? The numbers are not, they're not nice, they don't seem to follow any nice pattern, right? I mean, it's not clear. But Ramanujan observed something. I want to see if any one of you can see it. Maybe sometimes numbers are odd, sometimes numbers are even. Maybe can you make a prediction about that? Maybe something else. Okay, so let me ask you to see. Look at when you get the P of n divisible by 5. Can you see? When is it divisible by 5? For which n is Pn divisible by 5? 4, 9, 14, 19. Yeah. Do you see a pattern among these? So Ramanujan found that P of 5n minus 1 is divisible by 5. Okay, if you see 4, 9, these are not the only ones where there is divisible by 5. 4, 9, 14, 19, 24, 29, etc. You can see, you go all the way up to 200, you will see that this is always true. Okay, and so earlier, this is before the time computers were common, even calculators were common, right? So there were people, so at that time, do you know what a computer meant? Sorry? That's right. So a computer was a guy, a person, guy or a girl, whatever, a person whose job it was to compute things. okay, was to do calculations. So a computer was a real person, okay. So there were published books which there were books which just listed the number of partitions up to 10,000 or whatever, just numbers. So Ramanujan stared at those things and he found this pattern, okay. This you might say is sort of clear. I mean, divisibility by 5 is very easy to see, right? You just look at the last digit, it's kind of easy to see. Now I ask you to check for which n is p of n divisible by 7. Can you do that? So quickly, you probably cannot. So the other thing Ramanujan observed is p of 7n minus 2 is divisible by 7. P of 11n minus 5 is divisible by 11. Okay. These are, I mean, these are 11 also maybe you can see, but 7 is very hard, right? But he was able to see and observe these patterns and let me just say how you would prove such a thing. So the proof of 1 follows from the following generating function, sigma n equals 0 to infinity, n equals 1 to infinity, p of 5n minus 1 x power n. This generating function has is 5 times something, it does not really matter what it is. So product j equals 1 to infinity 1 minus x to the 5I power 5 divided by 1 minus j minus x to the j power 6. Whatever, it is something, but the important thing is that it is 5 times something. That will prove that everything in this expansion is divisible by 5. Right? So this is how one can prove such results. These are called congruence theorems, okay. And despite lot of effort, it took a long time before people could find other congruences. Okay. So the last theorem about partitions I want to state is the Rogers-Ramanujan. Okay. So we saw the odd equals distinct theorem, right? So when you see such a simple theorem with such a simple proof, you want to generalize it. Okay, then there are many ways of generalizing it. You can think of odd as partitions congruent to 1 mod 2, and then you can try to generalize that to 1 mod 3 or 2 mod 3 or whatever, you can try that. Or partitions not congruent, not divisible by 3, you can do various things. All of these have been done. But from the right hand side, the distinct, if you want to generalize, distinct means that successive parts differ by at least 1, right? Lambda I minus 1 is greater than or equal to 1. So a natural generalization is to lift that distinct condition to greater than or equal to 2. Right? I mean, it's natural. Okay. So there are two theorems. I'll maybe for lack of time only state the first one. So the number of partitions of n where successive parts differ by at least 2 is equal to the number of partitions of n into parts congruent to plus minus 1 mod 5. Okay. So if you think of the corresponding odd equals distinct, that would say at least 1 that would correspond to distinct, and this would be plus or 1 mod 2 that would be odd, right. So if you change this to 2, it becomes 5, not, I mean, and this was not completely clear, and so the proof of this is much more difficult. So proof not easy. It involves quite a bit of technology to prove such a result, and there is no bijective proof of this. Okay, no bijective proof. Okay, known yet. Okay, so this is considered a genuinely difficult problem. If you just change it a little bit, now I mean, I think it would be very hard for anyone to come up with a proof just from bare hands. Okay. Let me give you an example. So for small numbers, there's not enough data to look at it. So let's look at n equals 10. Okay. How many partitions are there of 10? You can see in your sheet. 42. But I only want, so I want to tell me, maybe let's do the easier part first. What are the partitions of 10 into parts congruent to plus minus 1 mod 5? Tell me one. 6, 4, good. Right? 6 is 1 mod 5, 4 is minus 1 mod 5. Next, anything else? That's all. No, there are a lot more. 9, 1, very good. I mean 1 is congruent to 1 mod 5, no? So you can do all ones. 1, 1, 1, 1. I will not write 10 ones. No. Anything else? No, this is this side, not that side. Just plus minus 1 mod. 4, 4, 1, 1. Exactly. 4, 1, 1, 1. You're missing one more. Exactly. 6, 1, 1. Huh? 5? No, 5 is 0. 5 is congruent to 0 mod 5. And let's look at the so this is RHS. And let's look at the left hand side. So I have 10, 9, 1. Right? Successive parts should have difference at least 2. But these are all okay. 8, 2, 7, 3, 6, 4. Anything else? 5? 5, 5, no, difference should be at least 2. One missing, and the hardest one to find is 6, 3, 1. Okay. So then the numbers are equal. Okay, so that's all I wanted to say about partitions. Now in the last few minutes, I want to tell you about plane partitions. Okay, so this is all, now I'm just telling you some stories, okay. So, but telling you how one can generalize partitions. So we saw the Young diagram of a partition, right. So let's say, what was it, 4, 2, 2, 1, we saw the 4, 2, 2, 1, right. This was a partition. So what you can think of, I mean one way of thinking of partitions is arranging boxes or in a two-dimensional room. So imagine, you know, flatland. Have you heard of flatland? So this is supposed to be some uh, two-dimensional creatures who live on the plane, right? We are three-dimensional objects, but you can imagine there are some two-dimensional objects that live on the plane. So there's some stories about this, and they live in flat land because it's flat. And so there is some room, and you have stacked boxes in a room. Okay, this is a two-dimensional room, and you are going to stack boxes in a room so that they are pushed in that direction. Okay, so you can generalize this to, okay, this room does not have a right angled corner, but let's say a usual room, or let's say that corner over there, there are, you know, 90 degrees, they meet like this, and you have the base. So you have three lines which meet. I mean, the corner of the room looks like this, and now we are going to have cubes, right? Unit cubes that we are going to stack. Okay, so you know they will look like so, right, etc. So each arrangement of this is called a plane partition because it's one level higher. So you know I'll do something. I'm not very good at drawing these things, but okay. So you get the idea, right? So I can do something like this, right? So this looks like an arrangement of 4 boxes in the corner of a room. So I can represent this as a filling of the Young diagram. So I take this Young diagram and I look from the top, I count how many boxes are there, how many cubes are there I look at the height of the cube at that given position, right. So at the corner I have 2 boxes, 2 cubes, here I have 1, here I have 1. So a plane partition is a representation like this where the numbers are weakly decreasing as I go. So for example, I can have a more complicated plane partition 4 3 3 1, 4 4 2, 3 1 2. Now this is an example of a plane partition. That means in this corner I have 4 boxes, then I have another 4 boxes, so on, and along each column and along each row the numbers are weakly decreasing. So a plane partition of n will be the number of such arrangements which sum to n. Okay, so that's an analog of that's a 3-dimensional analog of a partition, right. So so one of the nicest results about plane partitions is the number of plane partitions. So okay, so let me state the theorem. The number of plane partitions that fit inside an A by B by C room, let's say, is equal to the following product formula. Product I equals 1 to A, product J equals 1 to B, product K equals 1 to C, I plus J plus K minus 1 divided by I plus J plus K minus 2. And this is a theorem due to McMahon from the 1910s, I think. So McMahon also has an interesting story. He was in the English army and he was posted in India actually at some point. And after he went back, after he quit the army, he went back and said, I don't want to do all this, I'll do mathematics. So he wrote the first textbook on combinatorics actually. So that's due to him, and he found this beautiful formula for the number of plane partitions inside a room. Okay, you see how it's very symmetrically written, but there's a lot of cancellation, right? Because if I take k equal to 2, then there will be some cancellation, there will be some kind of telescopic factors. It's not written in the most optimal form, but it's okay. And let me just, Sushmita, can I take 2 more minutes? So I want, since we gave you this sheet with the triangular grid, I want to explain the connection of that sheet with this, okay, with plane partitions. So at the time, McMahon was thinking in terms of arrangements like this, but the modern view of this has to do with tilings. These are called lozenge tilings. Let me show you just for the 2 by 2 case. So 2 by 2 by 2 case, A equals B equals. Okay, can I just see how your sheet looks like? I just want to see whether the lines are horizontal. Okay, yeah, okay, so that's good, thank you. So we'll draw 2 by 2 by 2 hexagon. Okay, I apologize in advance. I'm very bad at drawing these things, but I hope you'll be able to see what's going on. No, sorry. That's all. Good. Okay, this is more or less okay. Not great, but okay. So you see, so this is, you see this inside your, I mean, there's this inside your sheet, right? You can make a 2 by 2 by 2 hexagon. So I want you to use your pens and mark off a 2 by 2 by 2 hexagon, which is a copy of this. Okay? So what we are going to do is we are going to tile it. So we have 3 kinds of objects called lozenges. So what are the lozenges? So lozenges are 2 contiguous triangles, okay, and there are 3 possible ways they can be arranged. One is this, like here, you see this? You see there are copies of this. Then you have this rhombus which faces in that direction. So there's like that, do you see that in your figure, like here? And then you have the lozenge which is a rhombus in the other direction. Okay? Okay, is this okay? So there are only 3 kinds of lozenges because every cell, every triangle is adjacent to 3 triangles. So this cell is adjacent to the one above, the one on the left and the one on the right. And similarly the upward facing triangle is adjacent to this, this and that, right. So now the goal is to tile meaning fit these lozenges into this so that every triangle is covered by exactly one lozenge and no triangles are left vacant. Okay, so let's do it. I think I'll need 3 colors. Okay, so let's do one and that should give you the idea of the connection. So let's say I tile this one like so, okay. Then I can tile this one like so, and then this is forced to be tiled like so, yes, and then this is forced to be tiled like so, and then I'll tile this one like so. Okay, and this one is like that, so I should use red. It's another red. This one is blue. This one is green. This one is blue. You see something magical is going to happen. Okay, so maybe I'll also color the interiors. So this is green, green here, red here, and blue here. Do you see? This has become a plane partition. So automatically your mind, I mean the way our mind works, we see in perspective. So this is the plane partition where there are two boxes of height 2 here, right? So the idea is that lozenge tilings of a hexagonal subset of the triangular grid correspond to plane partitions, okay, in a 1-to-1. And this is how, this is the modern way of proving results like this, okay? Okay, I'll stop here. Thank you. So I ask you to check that there are 20 ways of doing this, which is for I A equal to B equal to C equal to 2. If you do this, you will find 20 such tilings, and each one you will naturally visualize as a plane partition. Okay. Yeah.
Questions?
Yes?
My question is like part of the middle of the lecture, basically.
Okay.
It's with respect to the bijection you gave for the odd and distinct.
Okay.
So I want to know how we'll find an image for 7551. It's I mean, if I'm right, how we understood the method of constructing the images, you take if 5 and 5 are repeating, you club it together and you get. But
So you get 10, 7, 1.
But it's coming in the order 7, 10, 1. That's
No, no,
all.
that's okay. Yeah, yeah. You rearrange. Yeah. That's right. Yeah, I didn't say that, but yeah, you keep combining and you're rearranging, keep rearranging, and there is a slight issue there of being well defined. One has to show that no matter how you club things, you and I may be clubbing things differently, but we have to show that in each case you get the same partition. So all those things I kind of swept under the rug. But yeah, that's a good question. Yeah, one should check all those details. Yeah. Yeah.
Sir, up to now we've been parameterizing a partition as like a sum of some basically a sequence of numbers that sums up to n.
Correct.
So basically n has a partition.
Yeah.
So in plane partitions, so we still sum up to an n.
No, good question. So here this is all possible partitions that fit inside this. So that includes, yeah, so that's a very good question. So inside, so if I take, so let's take A equal to B equal to C equal to 2, right? So that means I should put 4 numbers here. So let's say A, B, C, D, such that A is greater than or equal to B and A is at most 2, that's the height of the room. And this is the length and the width, both are at most 2, greater than or equal to 0. Similarly, 2 is greater than or equal to A is greater than or equal to C is greater than or equal to 0 along this column. And along this row, C is greater than or equal to D is greater than or equal to 0. And along this row, B is greater than or equal to D is greater than or equal to 0. So you have to put 4 integers which A, B, C, D which satisfy these conditions. and I claim there will be 20 of them, and that will be exactly in correspondence with the 20 plane partitions.
So it's parameterized by 3 numbers, no, instead of 1.
Sorry?
So instead of basically having one number parameterizing it, now there are 3 numbers,
What are the 3?
A, B, and C.
No, but D is also there, no? The sum is not fixed.
Right.
So 0, 0, 0, 0 is allowed. So the empty partition is allowed. This is okay. Okay, so that's a very good point. So here we are not counting the number of plane partitions of n. So there is a theorem for that also, but I ran out of time, so I am not stating it.
Okay, so that brings us to the end of this 2-talk series. Thank you very much.
Thank you.
Let's thank the speaker again.